Presentation, yes. We have is from Master Builder Solution, and it's coming from Erik Yushai, sorry. Erik is a concrete fiber engineer and is responsible for the development and the technical support of fiber reinforced concrete at Master Builder Solutions.
And Benelux.
For Benelux. Okay.
Thank you very much. Welcome everybody. First and all, well, as I'm one of the last speakers, a lot of the stories which are included in my presentation have already been told, so I will need to go some brief faster so that I'm not falling too much into repetition, but I'll try to keep it as complete as possible, obviously. Well, we already have spoken about the performances of the UHPC, and thanks to its positive aspects, it is possible to reach some very extraordinary architectural feats. However, there is usually always actually a need for reinforcement. Our proposed reinforcement is synthetic structural fibers, more specifically micro and macro fibers, being the microfibers are PVA fibers and the macrofibers are polypropylene fibers. We are proponent of synthetic fibers as we believe that they have very great advantages thanks to their synthetic compounds. Basically, they are chemically inert. They have a high resistance towards solutions, acid and bases. They allow an easy and safe handling and contribute to very limited wear towards the mixing and transportation systems. In our range, we have various fiber lengths, which we can adapt actually to the various geometrical needs of elements. And with such a variation, we can even produce very thin elements. In our case, cocktails of polypropylene and PVA fibers, they give us actually a very cost-efficient optimization tool for the residual values. There is a different bonding mechanism between the PP and the PVA fiber with a cement matrix, and as such, we can use their proportions, basically how much of each other we use, to target specific areas of the residual values, if required, would be needed. We know that PVA will have a very high result on the FR1 value, whereas the PP fiber will have a higher impact actually on the FR3 value. There are further advantages of the synthetic fibers. They are flexible material which allow an easy finishing, and furthermore, they have also a positive impact on the reduced cracking caused by various mechanisms. Now, one of the reasons why synthetic fibers work so well is the fact that actually we have a structural fiber with a very low density, which means that we can have a very high amount of fibers per cubic meter. As an example, if we take about 30 kilograms per cubic meter of polypropylene fiber, we have there almost 3 million fibers per cubic meter. On the other hand, 10 kilograms of PVA fibers will amount to almost, well, to 7.5 million fibers per cubic meter. So this altogether gives a gigantic amount of fibers, creating a 3D network actually. And when we have a stable mixture, this is a must absolutely. Fibers will be present at every single section of the concrete element itself, so very near the surface as well. We are familiar with beton concrete covering that we need with traditional reinforcement. In this case, with fibers, we don't need to take into account a concrete covering, so the fibers will be present everywhere, actually, also very near to the surface, which means that when a crack occurs, the fibers will always start reacting immediately, so we don't need to wait the time until the crack reaches a few centimeters further for the traditional reinforcement. And that's one of the reasons why they actually work very well on reducing the cracking itself. Now, our approach at Master Builder Solutions is to provide a complete solution for our clients. This consists of concrete technology knowledge, thanks to our concrete technologies and also our advanced admission systems. We provide support with the installing of the dosing equipment if it's required. There are some differences between the traditional ones, the cyclone ones, and what you would need actually for synthetic fibers and more. And furthermore, we provide also support with the structural engineering behind it. So the engineering for the structural design is actually based, or we do it at least based on our software CivilMD, which is developed in accordance with European code for the traditional reinforcement part, as well as the FIB model code for the fiber reinforced part. And this gives us actually the tools to modify and tweak the entire ultra high performance concrete with fiber reinforcement to the specific needs of the client. Basically, we can change quite the DNA of the entire mixture itself, from the very start to the very end. Now, when we talk about fiber reinforced concrete, we will need to talk about flexural strengths and residual values. Important to know there are different production norms based on the type of the fiber. However, the European norm for testing the performance of the fiber reinforced concrete itself is the EN 14651, which is used, and actually that one is valid for all type of fibers. So if there is no difference which type of fiber you are putting into it, you are still taking concrete prisms, and after a certain maturation, usually 28 days taken as a standard, an incision will be made in the middle of the prism, right above actually where the measuring device is going to come. The measuring device is going to detect every development of the crack opening itself. We also call it the crack mouth opening distance, and the applied force is actually going to vary as such that we have a crack opening development of 0.2 millimeters per minute. So this one needs to remain a constant, and depending on the concrete mixture type, the fiber type and the fiber doses, you will need to apply more or less force as such that you don't develop too fast or too slow the crack mouth opening itself. Now, the explanation of the strain hardening, the strain softening has already been given, so I will just shortly say, depending on the mixture type, on the fiber type, and as well on the dosing, you can either fall within the strain softening pattern, where indeed the cracked concrete section has a lower tensile strength than the uncracked concrete itself, whereas starting from a certain dosing, again, depending on the type of fiber and depending on the mixture you have in there, you are going to reach a critical point where you see that the residual values are going to be well above the cracking moment of the concrete itself. And by residual values, for example, we have FR1, FR2, FR3, and FR4. They are, the first residual value is the force which is applied by the moment that we have reached crack mouth opening distance of 0.5 millimeter, FR2 with 1.5, and so forth. Basically, for UHPC, what we are going to generally have is a strain hardening system, where we indeed need to add additional force so that we have a higher crack opening. Now, we have already a lot of experience actually with the fiber reinforced UHPC, and I would like to share today with you some of our results which we have received, actually, which we have gotten with the Aalborg premix itself. It is important to notice that all the mixtures which I will be explaining here, they have actually been produced by using the Aalborg premixes as provided by Aalborg himself. We use the water dosing as recommended by Aalborg and Tom, as such to say that we did not add additional superplasticizers, which would also be a possibility to have greater workability and add more fibers. But for these tests, we only took premix plus water as indicated, plus fibers. Simple as that. The first mixture is actually the Aalborg Excel premix, and in here we added mustard fiber 235. It is a 30 millimeter polypropylene fiber, and we can already see that we have actually a clean strain hardening system. As we can see, we have a cracking force at 5.8 MPa, and further on it keeps increasing. It is important to notice that, of course, when we look, are we strain hardening or strain softening, we need to look into the characteristical values and not just the mean values. But in this case, we can see we have a very low coefficients of variancy, which means that our characteristical values were very near to the mean values. We got, and actually even within different prisms, we got a very homogeneous mixtures, which the results were very close to each other. And the reason is because we have such a high amount of fiber that we get some type of saturation, you can say, where the fibers will be actually quite uniformly redistributed. For mix 2, we use the Aalborg Extreme Light, and in here we decided to use some cocktails of the master fiber 235, the polypropylene fiber, as well, master fiber 401, and this one is a PVA fiber. Again, in here we can see that we have based on characteristical values a very nice strain hardening pattern. And we have a little bit higher, actually, as we have a combination of them both. We have even higher values, which we have gotten with the Excel mix. What we decided to do is to increase the dosing of the polypropylene fiber. So everything else was kept the same. We just increased the dosing of the polypropylene fiber. What we noticed is that in this case, we had a slight increase of the coefficients of variancy. But even so, the characteristical values are higher than what we had previously. And as such, again, we had a strain hardening system. Thanks to the stability actually provided by the Aalborg premix itself, we noticed that the workability and the stability of the mixture itself allowed us for more fibers to be added. So we saw our chance, and we increased furthermore the dosing of the master fiber 235 and the dosing of the master fiber 401. As such to say, we were looking a little bit for the limit of how much fibers can we add before we need super plasticizers. We could still push it further, but just with the indicated water dosing, how much further can we do? And this is almost the result where we ended actually. And in here again, we can see that we have an LOP limit of proportionality at about 7.66 MPa, and the FR1 value. By the time that we had a crack mouth opening distance of 0.5 millimeters, we were already characteristically speaking at 10.39, and for FR3 also 12.46. Again, we can see at the coefficients of variancy that these are very low, which actually the differences between the different prisms was very minimal. This type of coefficients of variance you can actually get only with very high dosaging, because when you have a standard strain softening patterns, the coefficients of variance is well above actually 15% usually, or even higher. Now, as a summary, basically what we can see is that the more fibers you add into it, the higher characteristical results you get, which is a little bit intuitive. On the other hand, what is very important is to still have a stable, workable mixture. If you have a segregated mixture, by then the differences in the different prisms will be so high that you will lose a lot of value. So as long as you keep it stable as a mixture, you can add more fibers until the limit is reached, and you will achieve better and higher results. To make it a little bit more visible, actually, I have included a very small case study, concrete slats, lamels. One of our clients, he intended to do some concrete slats 4.20 m by 20 cm and 8 cm thick with the Aalborg Extreme premix. Initially, his intention was to add 2 rebars of diameter 8 in there. However, for aesthetic and practical reasons, he wanted to see can this be switched to synthetic fiber reinforcement. And to do the job, actually, we went and did some calculations. The first calculation we did was to input the slat actually in one of our models of the Civil MV. It's a 3D model which works with a finite element method based on the model code calculations. We gave it in as being supported on 2 sides, which is pretty much a representation of how it will be installed. We were also requested to add the wind load in there, about 1 kilonewton per square meter. And we added our concrete mixture. The concrete mixture which we used for this case was actually mixture 4, which we have just seen. Now, after the result, after the computer has done the calculations in the background, you can extract a report of it, which we will see partially in here. It will always start with saying, okay, which parameters have we given it in, so the specific geometry, the chosen concrete mixture, the applied loads, etc. And at the end, what we want to achieve is to see, okay, the goal of the entire exercise is to see if the fiber reinforced concrete is sufficient to support the loads on its own. One way that it is shown is with the safety factor without reinforcement. Actually, the correct wording would be safety factor without traditional reinforcement, so without steel bars, because obviously the fibers themselves are the reinforcement in there. But as long as you have a safety factor which is higher than 1, it means that the fiber reinforced concrete can handle the loads on its own, as schematized in the program, obviously, without any need for steel rebars. It's not very clear on the screenshot, but actually we had everywhere safety factors well above 1. A second way that it is shown on the report as well is, again, the necessary steel bar reinforcement. And as we had a safety factor well above 1, it means that actually the area or the steel rebar area, it's 0. So we don't need to add any steel rebars in this case. So basically the conclusion for this one is, if we look into it as schematized, that the fiber reinforced concrete is well sufficient actually to carry the loads in the ultimate limit state. Another question was, okay, can we try and make some type of comparison? What happens if we add, what would we get pretty much with a steel rebar reinforcement on what we would get with a fiber reinforced concrete? There is another module actually, just to give an idea. It's a sectional analysis module, which we'll see to the internal forces and moments in the element. Basically, we schematized the element itself. We added the rebars in there. And for the concrete, I took a normal concrete in here for the C90-105, as it's part of the European code at Eurocode 2. The ultra high performance concrete is not part of the Eurocode 2. And this one works according to the calculations in here are, as this is pure traditional reinforcement concrete, it works according to the Eurocode 2. That's how it has been quoted in the background. And basically, using the formulas in the Eurocode 2, we could extract that, for example, for this specific one, we have a bending moment in ultimate limit state of about 1.64 kilonewton meter. This is the maximum moment that can be carried by the reinforcement before failure. Another information which we can extract as well, for example, is, okay, what is the cracking moment of the element, so when it is going to crack. And in this case, for the C90-105, actually, we got a bending moment of 1.1 kilonewton meter in a service limit state. When we do something similar with the fiber reinforced concrete itself, in here, this is based on the FIB model code. It's important also to realize that the formulas in the FIB model code, again, they make no distinction between what type of fiber it is. They only look at the residual results which you get from the testing method, 14,651, and those values are put into the exact formulas. And based on that, we did again the same geometry. We removed the reinforcement of the rebars, of course, and we added the Aalborg premix information in there. And once the calculations are done, we came up that in this case, the fiber reinforcement would provide a bending moment of 1.7 kilonewton meter in ultimate limit state, which was similar to what we got, in fact, with the C90-105. It's just to give an approximation so that both of them will be similar. Now, what is also important is to know that usually the steel bar reinforcement is a little bit overdimensionized because you are just limited in the section of the steel bar reinforcement which you can use. There are certain diameters of rebars, and that's that you cannot choose too much in between of them. And with fiber reinforcement, it is as we can manage the dosing very very specific actually. We can interpolate into it. It is easier to have a spot-on solution without having too much of reinforcement in there. And with everything else being already said, this was my presentation. Thank you very much.
Thank you. Are there any questions?
So the standard is for the testing itself, so it is the EN 14,651. It is a 3-point bending machine based indeed on the prisms itself, where you have a notch in the middle. There's a general standing for the European code.
The standard for the fiber or for the HPC? For the fiber.
For the not for UHPC, it's actually a standard for fiber reinforced concrete. So if you want to know what is the performance of a certain fiber dosing in a certain mixture, then that is the standard which you use.
And then what you want to describe the HPC build on your curves,
yes,
that you've shown. And then regarding the code of the program,
yes,
is it a known code or does it rely also to the
program
standard?
Yeah, the program itself in the code, when we have traditional reinforcement, is just the Eurocode 2. And when we have fiber reinforced concrete, is the FIB model code actually.
It's the FIB.
Yeah, it is just the FIB model code 2010.
Good. So there are no questions from the online audience anymore?
I had one more question.
Yeah, absolutely.
So you are proposing mostly the cocktail of fibers, PVA, PP.
Yes.
Do you also have experience with PE fibers?
Not in this specific range, actually. It's something that we don't market in the Benelux market. But as you showed in your presentation, if you just use PVA fibers, they are very intensive in the FR1 value, but because of their concrete mixture bonding, they will, after the FR1, FR2, they will lose their power very quick. And that's for that we use actually cocktails of PVA and PP fiber to have an overall performance.
Great.
Thank you.
One more question?
One more. Is the combination of Marketbills and Aalborg going to come up with some premix stuff in future?
Do you mean premix fibers included?
Yes.
That
Why not? I know Marketbills does it already.
We have spoken actually about this, Tom, and the reason behind this, what we would like to do is to make calculations project-based wise, because as you have seen, we have different values in there. And our intention is not to have over-dimensioning of it. It would be good to sell more fibers, obviously, but we don't want to load the client with more than it needs, because the fibers, of course, they have a certain cost, not only economical, but also practical. So we can create a premix and we can go with the heaviest one. Or we could go, for example, with the lowest one, but then again, how do we know which one is the right one for the specific client? It's way easier. We have the premix, we tell them the fiber dosing, and they just add that water. And it's actually the safest and most cost-effective solution for everybody.
it's better to have the flexibility for each project to adapt fiber dosage in function of application.
Especially at the start.
Great.
Okay, thanks.
Thanks a lot.
You learn to know everything about fibers.
We just want to challenge you.
How much fibers go in there?
Yes, that was, it's not by chance, it's not like I forgot it, we don't mind talking about specifics with the projects themselves, however, that information is kind of company knowledge, which is there gladly with our clients. Unfortunately for you, Hans, almost a competitor, so it's, we have
You can become a client.
you can become a client, you're very welcome for that. First buy and then with the, thank you everybody.
Thanks a lot. Again, super.